is kind of an introduction for welding. What you should know is we're talking about truss structure for aircraft where fuselages are constructed out of tubular steel. The primary steel that's used today is SAE 4130 steel. It's a molybdenum steel with about 1% chromium in it. In the general class, they covered materials and processes, and one of the steels that they talked about was this particular steel. By far, it's stronger than most of the other steels that are used, that could be used for aircraft construction. Previously, to the use of 4130 steel, they used a plain carbon steel, something like 1018, but that's a plain carbon steel. It's not alloyed with anything. So really, the strength of it is really from the carbon content in that steel only. In the case of SAE 4130, it's an alloyed steel with molybdenum being the primary alloy element in it, and it's got a moderate amount of carbon. It's only got 0.30% carbon. We know that by taking a look at the last two digits in the designation, so that's a relatively a moderate amount of carbon. It's considered to be weldable for both construction and for repair purposes in the field. Additionally, that steel, when it's used in aircraft, is usually in a condition that's called normalized. What that means is that it's been stress relieved. So the steel that you usually get is usually acquired in the end condition, which means normalized, which means stress relieved. There's some information for you in the old 9 Alpha book, the old general book, and also some information in the 4313 about this particular type of steel. It's about 4 times stronger in tensile strength than plain carbon steel. And it was a development pretty much out of Europe in the 1930s. Again, prior to this, we used SAE 1010 or 1018 steel. But the problem with it is that because it doesn't have the same strength, you're forced to use wall thicknesses and diameters that are generally larger than what would be desirable. When 4130 entered into use in aircraft, it significantly cuts the weight down of the aircraft because you get 4 times the amount of strength, tensile strength, as compared with mild steel. So again, it's a good choice for cross-constructed aircraft. Well, what do we mean by, or what are some of the other things that you should know? Well, firstly, defined in Part 43 Appendix A, you should know that anything that is been welded by the simple fact that we're welding to return it to service is considered to be an FAA major repair. The lead-in paragraph that describe a major repair says that anything that has to be repaired by the process of welding defines that particular repair as being a major repair. So it doesn't matter if you're doing maybe a landing gear leg that's made out of 4130 steel or a splice in aircraft that has to be fabricated by or repaired by welding. That, in fact, is a major repair as defined by the FAA. Something else you should know, too. You, as an airframe mechanic, can perform that major repair. But the only problem is you can't return it to service without an authorized inspector's signature that documents that it's been inspected. So you can do the repair, but the problem is you can't actually return it to service. That has to be done usually by an IA that signs a 337 form. Generally, we can repair tubing at any station and location in the aircraft. So if you look at major stations that have been developed in the aircraft by a drawing, any place in the tubing can be repaired either by splicing or by patching. For 4130 normalized tubing, the tensile strength is relatively strong. It's usually 80,000 to 90,000 psi tensile, and most of it is going to be in the normalized condition, which means stress relief. To stress relief, what they do is they heat the tubing up or the material up and allow it to cool and spill air. And what that does is it removes all of the manufacturing stresses from the tubing. Most of the tubing is also seamless as well. It doesn't have a seam in it, although we can purchase tubing that does have a seam. But all the tubing that we usually use is going to be seamless in its use. It's considered to be an air hardening material. It only loses about 10% of its strength after welding. And this is assuming we're using a mild steel rod or reinforcing rod, so you lose very little of its strength. The way that the tubing is sized is by its outside diameter and wall thickness. So when when you look in a catalog or you look in a structural repair manual, when they give or specify dimensions, usually the dimensions will are indexed in terms of the outside diameter of the tubing and the wall thickness. And the outside diameters are usually in 16th of an inch increments, and the wall thickness are usually in thousandths of an inch increments. You might have something like, I don't know, 5/8 inch diameter tubing with a 0.035 wall thickness. That would be something that would be relatively common. Anytime that you're going to be doing repairs, if the steel has been covered with any type of paint or primer, that's got to be removed before doing any type of repair work. So you have to have pretty much bare surface metal that you're going to be working with before you do any repair. Dimensions are usually given in terms of tubes or tube diameters. So they might list D just like they do with rivet spacing that will usually indicate D for rivet diameter. Well, what they do is they do the same thing in the case of tubing where it has to be spliced, or they'll usually indicate designation D to indicate tubing diameters, how much of a length that particular piece of sleeve has to be for making a repair. So use dimension D. There are several different types of welds that are used in tubing. One type of weld is a positioning weld to hold a sleeve in place. If, for example, we have to put a sleeve on a piece of tubing to kind of bridge an area that's been damaged, there's a positioning weld that's called a rosette weld. What they do is they drill a hole in the sleeve that's going to be placed on top of the tubing, and then they create a lap weld in that hole in order to fuse that sleeve in position it in place. It doesn't completely make for a repair, but what it does is it holds the sleeve in position. Usually, when they create rosette welds, there's a rule of the road regarding the size of that rosette weld. Whatever the outside diameter of the tubing is, the hole that is drilled in order to fill that area up with a kind of a spotted weld is about a quarter of the diameter of the tubing. So you can see here there's a couple of spots that are in the sleeve, and what they've done is they've positioned the sleeve over on top of the tubing, and then they've filled the holes in with weld material. And these are called rosettes, those are positions. Additionally, if we have to weld around the circumference of tubing, laps are commonly used. So you can see the sleeve itself has got a larger diameter than the original tubing. And what they've done is they've lap welded the circumference of that piece of tubing over the original structure in order to provide for the strength in the weld. So laps are fairly common. This is also interesting too. We generally don't have welds that run around the complete circumference just in a circle. Very commonly, the sleeves that are cut for welding with a lap joint are cut at an angle to give you more surface area for welding. So what we can do is on a miter box or with a special type of tubing cutter, we can cut an angle into the sleeves that allows us more surface area for welding. If they have just one cut in the tubing at an angle, usually it's cut at about 30 degrees, and they call that just a scarf cut. And again, to do that, what we would do is we would put the tubing, the sleeve, into a tool called a miter box. A miter box is a frame that holds the tubing in position with slits or cuts in it. And you run the hacksaw blade down the slit in order to create that 30-degree cut or that angle. Additionally, sometimes what they'll do is they'll make two cuts that are 180 degrees opposite of each other with 30-degree increments. It gives you an included angle of that cut of 60 degrees. They call it a fish mouth. So you'll see on this particular piece of sleeve, they've got a double 30-degree angle that's been cut into the tubing that gives you an included angle of 60 degrees. That's also done so that you have more surface area for welding. Butt welds are seldom used in construction or in repair work. The problem with using butt welds in tubing is you're only dealing with the thickness of the material when you're trying to bridge the material back together again by welding. So it gives you very little surface area for welding. So more commonly, most of the welds are going to be lap welds in aircraft for construction, for repair. You have much more surface area to deal with. You're dealing with more than just the thickness of the overall material when you're putting it together. Butt welds occasionally used, but seldom. Okay, that's what I can tell you. So those are the types of welds that we use for usually working in tubing. Preparation. Usually the tubing is covered by fabric. on a lot of the older aircraft like Arancas and Piper Cubs, what you'll find is that tubular structure has been covered with fabric. You have to be careful because the fabric itself may have coatings that are flammable. So if you're going to be doing repair work on aircraft, make sure that you remove enough of the fabric away from the repair area so you don't create a fire hazard. In the old days, they worked with aircraft dope and cotton, which was highly flammable. Today, the materials are less flammable, but nevertheless, you have to always be concerned with fire. So make sure that you have adequate precautions so that you don't cause a fire in the fabric or the coating system that was used for fabric covering. There's a few ways that the tubing can be cut if it has to be severed in any way. One way of doing it is, like I just mentioned, you can take a miter box and you can cut the tubing at a specified angle. Or another way of doing it is with a special type of device that goes into a drill press. What it does is it takes a hole saw and it kind of coats the tubing with half the diameter of the hole saw so that you get a perfect cut all around the piece of tubing. So that's a way for doing it. Also, you should know this too. When tubing is assembled, it's sometimes possible to have air trapped in the tubing structure. And as you're welding, the completion of that weld is going to be almost impossible because as the air is expanding, it's trying to escape from the tubing. So what they do is they provide a vent hole in a lot of tubing as part of either construction or repair. And then after the welding has been completed, they'll use a drive screw to kind of close the hole off. I'll talk to you more also about protection on the inside of the tubing to prevent from rust. But if you want to avoid the problem of air being trapped inside of the tubing that would prevent you from closing out a weld, well, one way of doing it is just having a vent hole that's open and again closing it off with a drive screw. Okay, later. The way that they prevent rust in the tubing when it's both in storage and in service, for many aircraft, they've coated the inside of the tubing with linseed. And you may say, well, couldn't we use other materials for protecting from rust? The answer is yes. However, probably a better material for preventing rust would be linseed oil. It's thick and viscous, and sometimes when you weld a piece of tubing, you'll see smoke coming out of either end of the tubing. What you're seeing is really the smoke from the linseed oil. It's usually replaced when we've done a repair. All you have to do is just fill the area up with linseed oil and then drain it through the vent hole, and then you can close that area off with a drive screw. That oil serves an additional purpose you might be interested in knowing about. If cracks develop adjacent to weld beads, the presence of oil that kind of soils or marks the fabric, that's an indication to you that maybe you've got a crack starting in a weld. So the tubing, the oil is there primarily as a rust preventative material. It prevents the tubing from rusting internally because it's a ferrous metal. But if you see oil seeping into the fabric cover of that tubing that's on top of it, you can better investigate to find out why there's oil there. My guess is that you've got a crack in a weld, and again, the oil is escaping through that area and it's soiling the fabric covering on top of the aircraft. Okay. So, some rules of the road regarding welding 4130. Generally, a black heat is required as a preheat before you weld, and we judge that by looking at the color of the steel as it's coming to temperature. So if you get to maybe a black heat, that means about 300 to 400 degrees Fahrenheit, and it probably will weld a little bit better if you do that. Also, there's some rules of the road that are a little bit different than welding in flat stock that you might want to observe in tubing. These rules come from Cessna when some of the aircraft, their AgCat in particular, had welded fuselage. They're looking for a bead width in tubing that's about twice the thickness of the wall. That's actually fairly narrow, but anything that would kind of approximate that would be okay. It doesn't have to be exceptionally wide. In flat stock, we're looking for a bead width that's about 3 to 5 times the material thickness. But in the case of tubing, what Cessna considers to be acceptable for their aircraft that are welded, for tubing anyway, we're talking about 2 times the thickness of the wall of the tubing. Also, you have to allow some clearance for joints to expand when you weld. There's a rule of the road, about a 1/16 of an inch clearance between parts that have to be welded to allow for adequate fusion. a swag. Many of the aircraft are tacked in jig structures where clearances can be controlled. They're taken out of the jig after they've been tacked, and then they're finished outside of the jig to prevent the structure from warping. But you do have to have some expansion space in the joints in most cases. If in fact you do have any butt joints in the tubing, and again it's rare to have butt joints when you assemble or repair, any butt joint has to have 100% penetration. You have to have the material actually melted through and fused completely through its thickness, because again, all you're dealing with is the thickness of the material in constructing the joint. So you have to have 100%. Any fillet weld, any lap, a minimum of 15% penetration, which seems marginal, but it's enough in SAE 4130. If we're talking about flat stock, fillet welds usually have a penetration range of maybe 25 to 50% of the material, but fillet welds, any type of lap and tubing, about 15% would be acceptable. The entire weld bead should look great. You should have perfect ripples in it that are evenly spaced, so the toes of the beads veer into the base metal perfectly. And it's difficult to do. Some of the welds are actually done quite well. I'll pass this around as kind of a sample of something that would be acceptable. Most of these stimulate either construction or repair for pieces of tubing. But if you look at the beads in that thing, it looks pretty good. This thing was oxyacetylene welded, the sample that I'm passing around. I've seen better welds done with TIG welding. However, those look actually pretty good. So there's some samples of different types of welded joints, and also welding technique was actually pretty darn good. Anything else? Any oxides that are created, they better not show up more than a ½ inch away from the weld. Again, this is kind of a standard rule for most welding. Any signs of porosity or blowholes are unacceptable. You're going to have to remove those by grinding the parent material away and re-welding. You're going to have they have to be removed from the airframe structure. No burning, no cracking, no pits, no distortion. All welding scale has to be removed by wire brushing. So again, it has to look good. Understand that this is going to, in most cases, the tubing is part of the structure for the aircraft. So, if somebody's flying it, it's going to have to be perfect. No filing or filling of welds with solder, brazed metal, or any other filler material. That causes loss of joint strength. The temptation is always there to try to make something look better cosmetically, but in essence, what you're doing is really weakening the joint by trying to braze over on top of it or fill in nasty-looking welds that don't actually fare into the metal very well. Never weld over an existing weld. You'll find that the metal has been metallurgically changed, and it's going to be very difficult to weld over that area. You'll cause a crack to occur, ultimately. So if you've got an area that's been welded that has to be, or an area that has to be re-welded, all of the old weld material has to be ground away in order to add new material in. So we never weld directly on top of a weld bead. Very poor practice to do that. So grinding and then re-welding. If you look at aircraft structure for tubing, there's two different kinds of versions for tubing in aircraft. One type of tubing that's used for truss structure would be called a Pratt truss. The other one is called a Warren truss. The Pratt truss is kind of identified because at the individual stations, what you're going to find are these members that connect the longerons together in kind of a box-like structure. You generally see this more commonly in Pratt type of structure. So you've got longerons that run the length of the fuselage, but you have these stays that are kind of positioned in between bays of the aircraft. And that kind of identifies the structure as being a Pratt type of truss. Originally, the Pratt truss, they had wooden longerons, and what they had were struts that carried compressive loads. And sometimes they even had piano wire that they used that kind of bridged the areas between the beams of the aircraft structure. But if it's going to be welded structure, it's all going to be SAE 4130 tubing. But again, to further identify this as a Pratt truss, look for the vertical and horizontal members that kind of separate the individual bays of the aircraft. It makes for a box-like structure for the aircraft. Other aircraft have what they call a Warren truss. The longerons are only connected by diagonal members that attach to the longerons themselves. So you can see you've got a series of kind of W's or isosceles triangles that kind of connect the individual pieces of longeron together. So that identifies that type of tubing as kind of a worn crust. Which one is better? Well, there's really no answer. They both take loads fairly well, but if you look at a lot of bridge construction for commercial purposes, they kind of follow the worn pattern. So if you look at trestle bridges on aircraft, generally the worn is generally the one that is commonly used. And it's more light, it's lighter because you don't have the individual stays that for the vertical and horizontal members that are part of the fuselage structure. In actuality, when you look at a lot of aircraft fuselages, it's kind of difficult to discern actually what you have. Maybe it would be combinations of both. If you can look at this one, I can identify the majority of this aircraft structure as being a Pratt truss because I can see the box-like structure of the tubing. There are some vertical elements that are in it, or I should say diagonals, but again, you can see the individual stations have been partitioned by those pieces of tubing to kind of make it look like a Pratt truss. If you look at maybe something like this, I see some of the Pratt characteristics in it, but I see some of the tubing kind of forming isosceles triangles, so maybe a portion of the tubing or a portion of the fuselage might be worn in its construction. But again, that's kind of what we're looking at inside of the aircraft with the skin removed. Again, some examples of different kinds of joints that we use in welding. A lot of the welds are cluster welds where pieces of tubing have been grouped together and they lap the tubing using fillet welds in order to join the tubing. So wherever you've got a grouping of tubing, something like this, verticals and diagonals that join into a longeron, we typically call that a cluster. You've got cluster welds that are used throughout the aircraft for some purposes. When aircraft fuselages have to be put together, usually they work in piece parts in a jig. So what they'll do is they'll tack up individual parts in a jig and then take it out of the jig and then complete the welding outside of it. That way they don't trap any of the stresses that would cause warpage. There's also some tricks of the trade too that some people like to do in tubular welding. They never weld completely around the circumference of the tubing. What they'll do is they'll quarter weld around the circumference. So for example, if I'm looking top down on a piece of tubing, when I'm welding it, the idea is not to weld completely around the circumference. They might segment this thing off into quadrants. So they might have a weld that kind of begins over here, and then they'll weld maybe a quadrant over here, and then what they'll do is they'll come back over here and weld this quadrant, and they'll come over here and finish it off over here. What that does is it spreads the stress out somewhat evenly so that the tubing doesn't end up bowed. So they call that technique quarter welding, and it's commonly done with a lot of tubing anyway. So it's called quarter welding. All right. Anything else? Well, there are some modern aircraft that are made out of tubular steel. Everybody thinks it's only really old aircraft. But if you look at some of the Cessna aircraft that are crop dusters, this is kind of what you find beneath the skin structure. A portion of the fuselage is welded tubular steel. The aft portion of it is semi-monocoque out of aluminum alloy. But for a lot of the crop dusters, we have both Cessna and Piper, the aircraft have to be sturdy. And one way of making the aircraft sturdy is by using tubular steel or a cage structure for the pilot and also to sustain being able to land on roads. Mostly, the landing gear also on these aircraft are made out of spring steel. It would be very difficult to construct an aircraft with an oleo strut that would withstand crop dusting use over an extended period of time. So you have to have something that's relatively beefy. So this is what they use as a crop duster in a lot of cases. Use some Cessna 188 ag wagon or an ag cat is common. The Piper 1E is similar. So if you look at that, similar construction, it uses a welded tubular structure for the fuselage. We also use welding for engine mounts in aircraft too. So occasionally you'll find, like with radial engines, mostly the structure has been welded together. They usually fabricate these things in jigs in order to maintain alignment of the tubing. So they'll tack it together and then subsequently take it out of the jig and then finish welding it outside of it. But a lot of the round engine mounts are welded out of 4130 tubular steel. That's one that's for radial engine. And here's one for an aircraft where they're going to be retrofitting a PT6 for the aircraft engine, but they needed a cradle that's relatively strong, so it's been fabricated out of 4132. We'll talk about inspection in a little bit, but what I kind of want to get into is maybe a little bit on what you have to do to tubing that's been damaged. Well, if you have to straighten tubing out before you do any work, one simple method is just to kind of gently coax it back into position by using, you can take like a channel iron and use that as a base, and then use a couple of blocks of wood as support, and with a C-clamp right at the apex of the bend, in many cases you can bend the tubing back into position. This may require no patching or anything, but as long as the tubing hasn't been crushed or crinkled or damaged in any other way, this is one way of straightening out tubing that is straightable. So you don't have any holes or cracks in it. Okay, we can straighten it back in position. So I'll show you a video in a little bit that demonstrates that technique. This is how we can get it back in position. No heat is required in most cases. You just have to have enough force, and you have to have blocks of wood that conform to the shape of the tubing in order to kind of push it back. So that's the idea. You'll have to allow for a little bit of spring back, just like you do when you bend aluminum alloy. But again, we can check it with a contour gauge in order to verify that the tubing is straight afterwards. That's what we can do. Okay. All right. For tubing that's out of round, we can coax that back into position as well too. You can take a couple of hardwood blocks that will work as forms, and with a great deal of force, what we can do is we can kind of take a contour back in a piece of tubing that's somewhat out of round. You can again check it with a contour gauge, but this is how we can correct that. So out of round tubing is corrected that way. So again, hardwood blocks, they use them and position them over the area that's been out of round. Squeeze like hell, and then you should be able to get the thing back in position. Well, what do we do if we've got something where the thing is going to go out of alignment because we've cut away a piece of tubing? Well, we have to hold the tubing in position or the rest of the structure in position by a homemade tool. I have one of these in my toolbox. I've used it once. But if you start to cut pieces of the tubing away, you're going to find that you have to maintain specific dimensions in order to fit a new piece of tubing in. This is called a jack, and really all it is a piece of scrap tubing that's got a threaded rod on the inside of it. What I can use that for is to kind of position between stations at welded areas and in order to hold alignment as I fit a new piece of tubing in position. And actually pretty simple to do. It's not difficult to do. If you want to see one in the shop tomorrow, I'll drag it out and show you. But the way it works is kind of like this. When you've got let's say a splice that has to be made, we'll prepare the area for splicing, but it's possible the rest of the structure can sag. So what they do is they install a jack at the station locations beneath it in order to kind of hold her in a fixed position. So I think you get the idea of kind of what you're doing. It just allows you to kind of prevent the structure from sagging and hold alignment. If you look at a lot of older aircraft blueprints, you can get the dimensions and you can check them with a trammel in order to verify that the dimensions are technically correct. But you need something to kind of hold or position in place. So we use a piece called a jack or a tubing jack. Well, let's first start talking about some of the repairs that are possible in tubing from damage. Well, if we have a hole in a piece of tubing, one thing that we can do is we can patch it. And the patch that they specify in 4313 kind of looks like a rectangular piece of metal that's been bent over the structure, and that's exactly what it is. But there's limitations on what can be repaired if you've got a hole. And what it tells you is for dents or holes in tubing, the maximum repair that can be created or repair that can be accommodated would be something that doesn't cover more than about a quarter of the circumference of the tubing. If it goes beyond that, you can't technically use this repair. Might another repair work? The answer is yes, but this specific repair will only be good for you if only maybe a quarter of the tubing diameter has been compromised. Also, it will work for dents, provided the dents are no deeper than a tenth of the tube diameter. What we do for doing this repair, you're going to have to lay out a piece of flat stock 4130, and what we're going to do is we're going to tack it to the sides or to the top of the tubing, and then we're going to coax it over with a little bit of heat in order to get it to conform. I think I've got one of these, as you can see what it looks like on this piece of tubing. So what they did is they took a rectangular piece of tubing of the appropriate dimensions, they tacked it in position, they bent it over with a little bit of heat, and they welded on opposite angles in order to create the weld, at least the cover for it. So, but it's called a welded patch. Sometimes longerons are damaged where they got a hole in it, either from rust or just a physical hole for other reasons. Sometimes landing gear legs are damaged either from corrosion or from rust or as a hole in it for other reasons. They can be repaired that way as well. Notice also that there are the limits that they get, or what they tell you. That dimension that they give you as 2A from the edge of the hole to the edge of the patch. A refers to the outside diameter of the tubing. So what they're telling you is if this is 1/8 or 1 inch diameter tubing, this dimension from here to here would be 2 inches. So that's what they're telling you in that illustration. The thickness of that piece of flat stock would approximate the wall thickness of the tubing. So